Welcome, deep divers, to another exploration into the frontiers of science. Today, we're tackling a question that might sound, well, a bit futuristic, but is actually one of the most pressing realities of our time. Can we really drink the ocean?
It's a great question to start with.
Think about it. For many of us, turning on the tap and having fresh, clean water flow out is just normal, something we absolutely take for granted.
An everyday convenience, really.
Exactly. But for a rapidly growing slice of the global population, clean water isn't a given at all. It's a profound challenge, sometimes a luxury, and often, an elusive dream.
And you really hit on a foundational issue there. This global water crisis, it goes way beyond just basic thirst. It's this really complex tapestry.
Woven with different threads.
Precisely. Threads of escalating population growth, which consistently, outpaces our existing freshwater resources. Then you add increasing industrialization, the accelerating impacts of climate change, which are undeniable, and widespread environmental pollution.
And it's not just the obvious pollution, right? Not just industrial spills.
No, not at all. Consider the really insidious problem of micropollutants.
Yeah.
These are like invisible chemicals, hormones, pharmaceuticals, pesticides, personal care products. Things that find their way into our water sources.
Even in tiny amounts.
Exactly. Even in incredibly tiny concentrations, they can have really significant detrimental effects, both on human health and on delicate ecosystems.
That is a sobering thought. And when you add in other complexities, like regions where even treated wastewater gets recycled back into agriculture, or sometimes even for indirect drinking water.
Right, which can amplify that contamination challenge.
Plus, managing really complex industrial wastewaters. I'm thinking oil and gas operations or coal power plants. That must be a whole different ballgame.
Oh, absolutely. Those industrial brines can have incredibly high levels of dissolved solids. Sometimes, 6 times saltier than seawater?
Wow.
And they often come with a high tendency for fouling membranes, which we'll get into. Plus, some new regulations are pushing for zero liquid discharge for these industrial wastewaters, or even for brine from inland desalination.
Zero liquid discharge, meaning they have to get rid of all the water.
Essentially, yeah.
Right.
Forcing us to develop technologies that can concentrate these feeds right down to solid salt. It's a huge technical hurdle.
So it's this multifaceted problem. It really demands innovative, large-scale solutions.
It does. And when you look at our planet, right, covered in these vast oceans, over 70% of the surface, it just naturally beggars the question.
Why aren't we just drinking seawater? Can we actually turn the ocean into a viable, drinkable resource?
That's the core question.
And that's the very heart of our deep dive today. We're going to explore the incredible science and engineering that's working hard to make that a widespread reality. The field of desalination.
Exactly.
And specifically, we'll be focusing on some cutting-edge advancements coming out of leading research institutions, places like the eNexus lab.
Ah, yes, eNexus.
The name itself gives you a clue, right? Their interdisciplinary focus. Energy, environment, and electrochemical interfaces.
Absolutely. The eNexus lab is really known for its pioneering work right at that intersection. Their mission isn't just, abstract science.
It's applied.
Very much so. At its core, it's about tackling some of the toughest, most fundamental challenges in clean energy and electrochemical innovation. And water purification, especially desalination, is absolutely central to that mission.
So we're talking about technologies that could genuinely change things.
We really are. Technologies with the potential to fundamentally change the world, quite literally providing clean water where it's most desperately needed. And for many of you listening, maybe you're early-stage college students starting out in engineering or environmental science, chemistry, materials science.
I'd like that.
Right. Understanding this field isn't just fascinating, it's actually pretty crucial. Your future studies, maybe even your careers, could very well connect directly with these innovations. Imagine being part of that.
So what's our mission for today's deep dive? We're going to try and systematically unpack the current state of desalination tech.
Where we are now.
Exactly. We'll look at the impressive progress, for sure, but also, honestly, explore its limitations. Some of them are quite surprising, quite stubborn. Then we'll journey into the really cutting-edge stuff, the new materials, the ingenious system designs that hold the promise of unlocking, an almost unlimited supply of fresh, clean water from sources we couldn't have dreamed of tapping before.
Think of this as your kind of behind-the-scenes look.
Yeah.
A peek at the intricate molecular-level science that goes into turning salt water into drinking water.
Giving us the key insights.
Yeah, we'll give you the essential insights into how we do it now, shed light on where the persistent challenges are, and hopefully reveal what amazing breakthroughs are still on the horizon. thanks to, revolutionary molecular engineering and some really clever system-wide strategies. It's a compelling story of human ingenuity, and we're really just scratching the surface today.
Sure.
One, the global water crisis and the rise of desalination.
Okay, let's start with the tough reality that really underscores why this is so urgent. The global water crisis, it's not some distant threat, is it? It's here, now, impacting billions. Right now, over a third of the world's population lives in countries officially classified as water-stressed.
Over a third. That's already huge.
And the projections are stark, almost alarming, really. By 2025, which is just around the corner, that figure is expected to jump to nearly 2/3 of humanity.
2/3.
And this isn't just about feeling thirsty. Water scarcity casts this long shadow over pretty much every aspect of society: economic vitality, public health, national security, and critically, the delicate balance of our ecosystems.
Indeed, it really is a foundational issue. It underpins sustainable development everywhere. And while things like rigorous water conservation, fixing leaky pipes, improving catchment, those are absolutely vital.
We have to do those things.
We have to pursue them relentlessly. But fundamentally, they only optimize the water resources we already have. They help us use what's there more efficiently.
We don't make more water.
Exactly. They don't increase the overall supply. To actually augment our water supply beyond what the natural water cycle gives us, especially with growing populations and demands, we're basically left with two main large-scale options.
Okay, what are they?
The first is water reuse, which is essentially advanced recycling of wastewater.
Right.
The second, and our focus today, is desalination, which lets us draw from otherwise unusable salty sources, mostly the ocean.
And desalination, especially from seawater, it just sounds so compelling, doesn't it?
It does have a unique appeal.
It offers this promise of a virtually unlimited, steady supply of high-quality water, independent of rainfall, independent of dwindling groundwater.
It's a potential game changer.
Because it doesn't deplete our natural freshwater ecosystems, our rivers, our overstressed aquifers. For coastal areas, the logic seems obvious.
Makes perfect sense there.
But even inland, you mentioned brackish groundwater desalination is an option.
It is, yes. Though, as I hinted, managing the super concentrated brine that's left over, that poses its own significant challenges, both technical and environmental.
Right, the disposal issue.
To give a bit of historical context, if we look back a few decades, the early large-scale desalination plants, especially those pioneered in arid places like the Gulf countries, they mostly relied on what's called thermal desalination.
Thermal, so using heat.
Exactly. It basically mimicked the natural water cycle on an industrial scale. It involved heating huge amounts of seawater to make vapor, and then carefully condensing that evaporated, purified water back into liquid. Think of it like a massive, very sophisticated distillation setup.
Okay, I can picture that. But the energy needed, heating that much water, must have been enormous.
Precisely. Those early thermal plants were incredibly energy intensive. They consume substantial amounts of both thermal and electric energy.
And if that energy came from fossil fuels...
Which it often did, yes. That translated directly into significant greenhouse gas emissions. So it created a different kind of environmental burden. They were a solution, but a costly one, economically and ecologically.
So when did the technology start to shift? When did we find a better way?
The real paradigm shift happened over the last, say, 2 to 3 decades, with the rapid global growth and widespread adoption of reverse osmosis, RO technology.
RO. That's the term we hear a lot now.
It is. It has truly revolutionized the field. RO is now, by far, the main method for desalination worldwide. It accounts for roughly 70% of global desalinated water production.
70%.
It represents this monumental leap forward in energy efficiency compared to those thermal methods. Modern RO is so efficient, it's now the undisputed benchmark. Any new desalination tech being developed today is compared against RO.
How much more efficient are we talking?
Modern RO plants can consume as much as 5 times less energy than those early thermal approaches. It's a huge difference. 2. Reverse osmosis, the current benchmark for desalination.
Okay, so let's peel back the layers on reverse osmosis. How does it actually work? How does it manage to separate water from salt so efficiently? What's the core mechanism?
Well, to really get RO, we need to move beyond the simple idea of like a physical sieve with tiny holes. That's not quite it.
Okay.
RO operates on a much more nuanced principle called solution diffusion.
Solution diffusion.
Right. Imagine the membrane not as a sieve, but as this dense, semi-permeable film, usually made of a sophisticated polymer. Now, water molecules, they're very small, they're polar. They actually have a natural affinity for this polymer material.
Because they kind of like it.
In a way, yes. Under immense pressure, the water molecules first dissolve into the membrane's selective layer.
They go into the membrane material.
Yes. Once dissolved, they then diffuse through the polymer network. They're essentially wiggling their way across, moving from an area of higher chemical potential, the salty, pressurized side, to an area of lower chemical potential, the pure water side.
Okay, I think I follow. Dissolve, diffuse.
And then finally, they desorb from the other side into the purified water stream.
So it's this process where the water molecules are literally moving through the material itself, not just finding pores. That's fascinating. What about the salt ions?
Exactly. The salt ions, being larger and usually charged, have a much lower solubility and diffusivity in that dense polymer material. They're essentially rejected right at the surface. They can't easily dissolve into or diffuse through the membrane layer.
So they get left behind.
They do. To make this happen, seawater is continuously pressurized against this membrane. This applied pressure forces the water molecules across, while the vast majority of salts and other impurities are held back on the feed side.
And the result is?
Pure water, which we call permeates, and a highly concentrated saltwater solution, the brine or concentrate, which then needs to be dealt with.
The journey of RO in terms of energy efficiency sounds incredible. You mentioned a huge drop over the last few decades. How dramatic was that improvement?
Oh, it's been phenomenal. Back in the 1970s, the core RO process took about 10 kilowatt hours for every cubic meter of water produced.
10.
Today, that number has plummeted to around 2 kilowatt hours per cubic meter.
From 10 down to 2. That's huge.
It's a revolution, driven by a combination of things: developing much higher performance membranes, much more efficient pumps, and critically, the widespread use of energy recovery devices.
Energy recovery devices, how do those work?
They're quite ingenious, actually. They capture a big chunk of the hydraulic energy from the outgoing high-pressure brine stream.
The stuff that's leaving the system.
Exactly. And they use that captured energy to help pressurize the incoming feed water. This significantly reduces the net energy you have to put into the system.
Wow, okay. That sounds incredibly efficient. But I've heard about something called the thermodynamic limit. What is that, and how close are we actually getting to it?
That's a really crucial concept. The thermodynamic limit represents the absolute theoretical minimum amount of energy required to separate pure water from seawater. Doesn't matter what technology you use.
Like a law of physics limit.
Pretty much.
Yeah.
Imagine it as the fundamental energy cost of unmixing water and salt. It's related to the free energy of mixing, just in reverse. For typical seawater, about 35 grams of salt per liter, and assuming you recover 50% of the water from the feed.
Okay.
This theoretical minimum energy is astonishingly low, about 1.06 kilowatt hours per cubic meter.
1.06. Okay, so if the absolute minimum is 1.06 kilowatt hour, and you said current plants run around 2 kilowatt hour, there's still a gap there. Why aren't we right at that theoretical limit? What accounts for the difference?
That's where practical engineering kind of bumps up against theoretical physics. While 1.06 is the absolute thermodynamic floor, the practical minimum for a really well-optimized single-stage RO system is actually closer to 1.56 kilowatt hour.
Okay, why the difference between theoretical and practical minimums?
It comes down to the mechanics of the RO process itself. As you push water across the membrane, the brine left on the feed side gets more and more concentrated.
You're right. Makes sense. More salty.
And as it gets saltier, its osmotic pressure increases. You have to apply pressure that's greater than the osmotic pressure of the concentrate that's leaving the system at the end.
Otherwise, water wouldn't flow.
Exactly.
Uh-huh.
Even if you had a miracle membrane that was infinitely permeable, you'd still need significant pressure just to overcome the osmotic pressure of that increasingly salty brine. It's a fundamental physical barrier you can't avoid in the process.
So wait, if I'm getting this right, just making membranes even more permeable, letting water through even faster beyond a certain point wouldn't dramatically cut the energy needed for the main desalination step itself?
Precisely. This is a critical insight that's often missed outside the field. Once you reach a certain level of permeability, making membranes even more permeable has a surprisingly negligible effect on reducing the primary energy use for the desalination step.
Negligible? Like how small?
We're talking less than a 2% decrease in energy, even for a massive hypothetical jump in permeability. The energy is overwhelmingly dictated by the need to overcome the osmotic pressure of that concentrate. So the sort of low-hanging fruit for just making membranes more permeable has largely been picked already.
That's genuinely fascinating. It completely shifts where the focus for innovation should be. So if the core RO process itself is getting close to its practical energy limit, where is the rest of the energy actually going? Where should future efforts for big efficiency gains really concentrate?
This is indeed the million-dollar question for the next generation of desalination. A significant chunk of energy, often well over 1 kilowatt or gelashite, sometimes more, isn't consumed in the core RO separation at all.
It's used elsewhere in the plant.
Exactly, in the ancillary stages. We're talking about the energy needed for the seawater intake system, then the extensive, often complex, pretreatment processes.
Pre-treatment, like filtering out gunk.
Right. Removing suspended solids, algae, bacteria, other impurities before the water even hits those delicate RO membranes. Then there's post-treatment, maybe further purifying the desalinated water for specific uses, like removing trace boron for agriculture or adjusting the pH for drinking water.
Okay.
And finally, the energy used for brine discharge. Of all these, the pretreatment of the raw seawater is often the biggest energy consumer.
And things like getting boron out for crops, that takes extra energy too.
Oh, yes. Reducing problematic ions like boron or chloride down to levels safe for sensitive crops can sometimes need additional energy-intensive RO passes, adding significantly to both the total energy use and the overall capital cost of the plant.
So the big takeaway here, the real substantial energy savings for the future aren't likely to come just from making RO membranes more permeable.
Not primarily, no. The big gains will come from dramatically optimizing, streamlining, and maybe even integrating these other stages, especially pretreatment and post-treatment. That's where the major potential for savings lies now. 3. Major hurdles for current desalination membranes. The permeability selectivity trade-off and fouling.
Okay, that leads perfectly into the inherent limitations that current desalination membranes still face. Even with all this progress, one of the most fundamental challenges is something scientists call the permeability selectivity trade-off. Can you break that down for us?
Yeah, it's a really foundational concept in membrane science. You could almost call it a universal law for filtration. For the ideal membrane, you want two things that kind of pull in opposite directions.
Aye.
You want high water permeability, meaning lots of water flows through quickly. And at the same time, you want high selectivity, meaning it rigorously blocks all the unwanted stuff, like salt ions, micropollutants, boron, you name it.
High flow, perfect blocking. Sounds ideal.
It is ideal. But, like in so many areas of engineering and material science, getting both at the same time is incredibly difficult. It's often a real balancing act. You push for more of one, you usually sacrifice some of the other.
So it's a trade-off. More flow might mean more salt gets through.
Exactly. This challenge is often visualized in diagrams called Robeson plots, especially in fields like gas separation. But the principle holds for water too. Generally, if you design a membrane to be more permeable to water, letting water molecules pass more easily, it tends to become less selective.
Meaning more unwanted salts sneak through.
Precisely. For our current gold standard membranes, the thin film composite, or TFC polyamide ones, if we tried to significantly boost their selectivity for those really small, tricky salts, like tiny neutral molecules, boron, certain pharmaceutical residues.
Ones that are hard to remove.
Yes. If we tweak the membrane to grab those better, we would inevitably substantially reduce its water permeability.
And lower permeability
Means higher energy consumption for the whole process, ironically.
Right.
Because you'd need to either apply more pressure or use a much bigger membrane area to get the same amount of water. It's because their underlying solution diffusion mechanism fundamentally links permeability and selectivity. You can't easily optimize one without affecting the other.
So it's not just about pushing more water through faster, it's about pushing smarter water through. We need membranes that can somehow precisely pick out water molecules while leaving behind even those trickiest impurities, the small neutral ones that current methods struggle with.
Absolutely. And that leads us right into the second major, persistent headache in desalination. The pervasive problem of fouling.
Ah, yes. The dirty truth about membranes, they get dirty. Fouling is basically just stuff accumulating on the membrane surface or inside its pores, right? And for anyone running a desalination plant, it sounds like a constant battle.
It truly is a constant nagging headache, as you say.
Yeah.
And fouling isn't just one thing. It comes in several different flavors, each with its own challenges.
Okay, like what?
Well, first there's organic fouling. That's the absorption of dissolved organic stuff, think humic acids from decaying plants, or proteins, polysaccharides.
Okay.
Then there's scaling. That's the deposition, the precipitation of inorganic salts from the now concentrated brine solution, like lime scale in your kettle, but happening microscopically on or in the membrane.
Got it.
And finally, maybe the most insidious kind is biofouling. This is the growth and spread of microorganisms, bacteria, algae forming these sticky, slimy biofilms right on the membrane surface.
Biofilms. Nasty stuff. And the consequences of all this fouling, they're pretty serious, I take it, not just a minor annoyance.
Oh, far from it. It's a cascade of problems. Fouling significantly degrades membrane performance in several ways. First, you get a substantial drop in water production. The flow just slows right down.
Less water out.
Right. And often you also get a decrease in the quality of the purified water as the membrane selectivity gets compromised by the fouling layer.
So lower quantity and quality.
Exactly. To counteract that reduced flow, operators have to crank up the applied pressure, which directly means higher energy consumption and higher operating costs.
Makes sense.
Plus, fouling means you had to do frequent and often harsh chemical cleaning. These cleaning cycles aren't great environmentally, using chemicals, producing waste, and the harsh chemicals themselves inevitably shorten the membrane's lifespan. So higher replacement costs, more plant downtime. It all adds up.
So why are our current membranes, these advanced TFC ones, so susceptible to getting fouled up all the time? What makes them such easy targets for all this gunk?
It really comes down to their intrinsic material properties and their surface structure. Those gold standard TFC polyimide membranes, they're particularly prone to it for a few key reasons.
Okay.
Firstly, their characteristic surface topography. They often have this ridge and valley roughness, especially the ones made using amphenylamine or MPD. This roughness dramatically increases the effective surface area.
More places for stuff to stick?
Yeah. Exactly. More nooks and crannies, more attachment points for flauns to grab onto and build up. Secondly, these membranes are typically quite hydrophobic. They tend to repel water molecules a bit.
Which sounds weird for a water filter.
It does, but that property actually tends to attract organic and biological flauns, which are often nonpolar or have hydrophobic bits themselves.
Ah, okay.
And finally, their surface charge plays a role. The polyimide layer usually has negatively charged groups, carboxyl groups. These negative charges can actually make fouling worse in some cases, like promoting the binding of negatively charged organic flauns via positively charged calcium ions acting as bridges, effectively gluing the flauns on.
Wow. So the surface roughness, the hydrophobicity, the charge, it all conspires against keeping them clean. What about other membrane types, like for ultrafiltration?
Similar issues often apply. Conventional ultrafiltration UF or microfiltration MF membranes are frequently made from hydrophobic synthetic polymers too, which also promotes fouling. And a key issue with them is often their polydispersed pore size distribution.
Meaning the pores aren't all the same size?
Right, there's a wide variation.
Yeah.
This can lead to irreversible fouling because the larger pores can allow flauns to penetrate deep inside the membrane structure, making them incredibly difficult to remove by cleaning. They get lodged in there permanently.
So the bottom line seems to be developing membranes that are inherently resistant to fouling, that have a low fouling propensity. That's not just a nice-to-have improvement. It's absolutely critical for making desalination truly efficient, economical, and sustainable long-term.
I couldn't have said it better myself.
Yeah.
It's a central challenge for the field. 4, engineering the future. Molecular-level design of next-generation membranes.
Okay, this brings us to the really exciting part looking forward. How are researchers actually engineering the next generation of membranes to overcome these hurdles? You mentioned a kind of paradigm shift, moving away from that sort of random solution diffusion.
Right, where molecules kind of wiggle through the polymer network.
Towards something much more precise, like molecular sieving or size exclusion.
Exactly. The idea is to design membranes with incredibly precise, incredibly uniform pores or channels that can literally sieve out unwanted molecules based purely on their size and shape, like a perfect filter at the molecular scale.
That sounds like molecular level design.
That's precisely the term. It's about building membranes literally from the ground up, molecule by molecule, achieving unprecedented, almost atomic level control over how water and solutes move through. The grand vision here is creating specialized water channels.
Channels just for water.
Yes, so perfectly designed, they literally only let water molecules pass through, maybe even in single file, while meticulously excluding everything else, even molecules that are only fractionally larger. Imagine designing the perfect molecular bouncer for a very, very exclusive club. Only water gets in.
And what's amazing is nature kind of already figured this out, didn't it? We can look to biology for inspiration here. Tell us about aquaporins.
Aquaporins are honestly biological marvels. These are highly specialized protein channels found in the cell membranes of almost all living things, bacteria, plants, animals.
What makes them so special?
They are astonishingly efficient at transporting water and incredibly selective. They let water zip through incredibly fast while rejecting almost everything else.
Hmm.
Their unique structure is the key. They have this kind of hourglass shape.
Hourglass.
Yeah, with a very narrow hydrophobic center. It measures only about 0.28 nanometers across, which is remarkably almost the exact size of a single water molecule.
Wow.
And what's more, right at that narrowest point, that constriction, they feature a fixed positive charge. This precise charged bottleneck creates a high energy barrier. Water molecules, being neutral and small, can pass through with incredibly high permeability, almost no friction. But it rigorously rejects ions, protons, even small neutral solutes like urea.
Urea, that's tricky for current membranes, right?
Exactly. Aquaporins reject precisely the kinds of problematic impurities that conventional desalination membranes often struggle with.
So nature basically gave us the blueprint for the perfect water filter. Why aren't all desalination plants using aquaporin membranes then? What are the big challenges?
Well, while they're theoretically amazing, fabricating stable, defect-free aquaporin-based membranes on a large industrial scale has proven incredibly difficult.
Defect-free is the key.
Absolutely. The common approach is to put isolated aquaporin proteins into tiny lipid or polymer bubbles called vesicles, and then trying to get these to spread out perfectly on a support membrane to form a continuous layer. But achieving that perfection, that's the hard part.
What goes wrong?
Defects. Things like unruptured vesicles or gaps in the layer. These create leaks, which lead to poor salt rejection. Current experimental reports show salt rejections may be up to 98%.
Which sounds good, but isn't good enough.
Not for high-quality drinking water from seawater, no. You typically need 99.5% rejection, or even higher. Plus, there are questions about the long-term stability of that delicate lipid or polymer layer, and the stability of the protein itself under harsh industrial conditions. Proteins can degrade.
Okay, so direct use of biology is tough. Are researchers then trying to build artificial water channels from scratch? Mimicking aquaporins, but maybe making them tougher and easier to scale up? That sounds incredibly ambitious.
It is ambitious, and is where some of the most groundbreaking, conceptually exciting research is happening. Let's look at a couple of examples. First, carbon nanotubes, CNTs.
Ah, CNTs. Heard a lot about those.
Structurally, they seem simple, just rolled up sheets of graphene. But molecular dynamic simulations predict truly astonishing ultra-fast water conduction through them.
How fast are we talking?
Like 3 to 5 orders of magnitude higher water transport than conventional fluid dynamics models would predict. It's thought to be due to their atomically smooth, non-polar interior. Water just glides through almost frictionless.
Incredible. And can they reject salt?
Simulations suggest that very small ones, specifically 6-6 CNTs, with an inner diameter of just 0.47 nanometers, could theoretically achieve complete salt rejection.
Okay, simulations look great. What about real-world experiments? Are we seeing this performance in desalination yet?
Unfortunately, not really for desalination, at least not at scale. Experiments have largely confirmed the fast water flow, which is great. But the CNT membranes made so far typically only reject particles around 2 nanometers in size.
2 nanometers. That's much bigger than a salt ion.
Exactly. Puts them squarely in the ultrafiltration UF range. Good for viruses, maybe large molecules, but not selective enough to separate individual salt ions for desalination.
So what's the main hurdle for CNTs?
The holy grail, really, is twofold.
Yeah.
First, consistently making highly monodisperse, meaning perfectly uniform in size, small diameter CNTs. And second, crucially, integrating them perfectly upright and defect-free into a robust, large-scale membrane without any gaps or leaks. It's a massive materials engineering challenge.
Got it. What about other types of artificial nanochannels, where researchers have maybe even more control over the design?
Yes, that's another exciting direction. These offer more customization. They might not have the perfect smoothness of CNTs, but their chemistry and pore size can be precisely controlled during synthesis.
Like what kind of structures?
Well, there's a class called supramolecular synthetic nanochannels. Examples include modified cyclic peptide nanotubes, or things called ethylene nanotubes.
Pretty names.
Indeed. Both are formed by the clever self-assembly of specially designed ring-shaped molecules, which stack up precisely to create a channel. Scientists have designed these with incredibly small, uniform pore widths, down to 0.47 or 0.64 nanometers.
Close to aquaporin size.
Exactly. And those ethylene nanotubes, for instance, experimentally showed they could reject sodium, potassium, and chloride ions, while still letting water through quickly when the channel was open.
Ah, there's a catch. When it was open.
Yes. Here's the critical issue with that specific example. These channels were only open or conducting water about 5% of the time. Their structure was dynamic, fluctuating. So this flickering led to a very low average water permeability, much lower than current TFC membranes, making them impractical for high-volume desalination right now.
So it really is that double challenge then. Designing the perfect selective channel at the molecular level is one thing.
Right. Getting the transport properties exactly right.
But then you also have to figure out how to build it so water flows continuously and assemble millions or billions of them perfectly on a large, robust, scalable platform.
Exactly. It's simultaneously a challenge in molecular synthesis and a monumental challenge in scalable, defect-free assembly and integration into membranes that can handle real-world operating pressures and conditions.
This seems like a good point to talk about another approach, building materials from the bottom up. What about materials that can spontaneously organize themselves into precisely patterned structures? That sounds like a dream for controlling pore size uniformly.
This is a truly fascinating area, focusing on what are called self-assembled materials, sometimes referred to as ordered amorphous or soft materials. These materials, they can be either relatively small molecules or larger things called block copolymers.
Block polymers.
Yeah, think of long polymer chains made of two or more different types of blocks chemically linked together. These materials have this unique ability to spontaneously organize themselves into highly ordered repeating structures called mesophases.
And the pores are formed by these ordered structures.
Precisely. The pathways for water transport are exquisitely defined by these self-organized microdomains. This offers a huge advantage over conventional membranes because you can achieve incredibly narrow, uniform pore size distributions. A level of control that's almost impossible with traditional polymer casting methods, which tend to give a wider range of pore sizes.
What kind of pore sizes can these self-assembled materials make? Can they get small enough for desalination?
They can be tuned quite well. Block copolymers typically form pores in the 5 to 50 nanometer range, which makes them great for ultrafiltration. But for the really demanding job of desalination, researchers are focusing on carefully designed small molecules. These can self-assemble into structures with much finer pores, typically ranging from 0.5 to 2 nanometers.
Ah, right in the sweet spot for RO or nanofiltration.
Exactly. There's been really significant progress recently in designing these small molecule membranes specifically for desalination. Some experimental systems have achieved impressive results, like 95% ACL rejection, using highly uniform 0.75 nanometer pores.
That sounds promising. What are the keys to making these work well?
A few key things. You need to make these selective layers incredibly thin, ideally around 30 nanometers thick, similar to current TFC membranes, to allow high water flow. And you need to ensure the self-assembled pores are perfectly straight and run continuously right through the membrane thickness. Any blockages or twists would slow things down.
And making sure they line up right.
Yes, that's crucial. Researchers are actively developing scalable methods to direct the self-assembly process, using things like magnetic fields or clever soft confinement techniques to make sure these tiny pores orient vertically, straight up and down through the membrane. That's essential for maximizing the water flux.
Okay, now I have to talk about the material that seems to pop up everywhere. Graphene. Atomically thin, super strong, super smooth. What's its potential role in desalination?
Graphene. Yes, it holds immense promise for membrane separations, desalination included. It's being explored mainly in two different forms for this.
Okay.
First, there's netochorous graphene. The idea here is to take a pristine single layer of graphene, just one atom thick, and introduce incredibly tiny, precisely sized defects or pores into it.
Like punching adder-sized holes in it.
Kind of, yeah.
Yeah.
Molecular dynamics simulations predict absolutely astonishing performance for membranes like this. Theoretical water permeability potentially 100 to 1,000 times greater than current TFC membranes, especially for pores around 0.45 nanometers across that have hydroxyl groups around the edges. And theoretically, complete salt rejection.
1,000 times faster and perfect rejection. That sounds like the ultimate membrane. Has this been shown experimentally?
Well, that level of performance was recently demonstrated impressively, but on a very, very small scale.
Yeah.
A proof of concept sample, maybe only 5 micrometers across.
5 micrometers. Tiny. So what are the massive hurdles to making, say, square meters of this stuff for a real plant?
That is the billion-dollar question, isn't it? The biggest hurdle, undeniably, is scaling this up. You need to create large area, perfectly defect-free single sheets of graphene. Then you need to reliably punch trillions of uniformly sized nanopores across that entire area. And you need to do it all cheaply enough to be viable. Current methods for making precise pours are often slow and expensive.
But even if we could make it perfectly, there's that other point you made earlier.
Exactly. Even if we overcome the manufacturing challenges, remember that just increasing water permeability for the RO step itself has limited benefit above current TFC levels. The energy needed is dominated by osmotic pressure, not membrane resistance, beyond a point.
So unless these graphene pores are also super selective.
Right. Unless they can be tuned exquisitely finely to also reject those small neutral solutes, like boron that TFC membranes struggle with. Nanoporous graphene might actually be at a disadvantage compared to much cheaper existing TFC membranes, despite its incredible permeability. The real game changer would be if it offered both ultra-high permeability and ultra-high selectivity for those specific tricky molecules.
Okay, makes sense. What about the second form you mentioned? Graphene-based frameworks. How are they different?
These are structurally quite distinct from single-layer nanoporous graphene. Graphene-based frameworks are typically multi-layered stacks of graphene sheets, often made from graphene oxide or GECO, which is easier to process. These sheets are then assembled into a macroscopic membrane.
So stacks of sheets, not single sheets with holes.
Correct. Water moves through the tiny gaps between the stacked layers, and it permeates incredibly fast through these frameworks, mainly due to something called slip flow along the atomically smooth graphene surfaces. Water molecules just glide with very little resistance.
Sounds fast. But what about selectivity and stability?
That's the current limitation. A major issue is that the spacing between these graphene oxide layers actually expands when the membrane gets wet. In humid air, the gap might be around 0.9 nanometers, but dunk it in water, and it can swell up to 1.3 nanometers or even more.
Why does it swell?
Because water molecules get in between the layers, and there are repulsive forces between the oxygen-containing groups on the GECO sheets. This expanded spacing makes the channels too wide to effectively reject small salt ions, like sodium or chloride. So they're not suitable for full desalination right now.
And stability.
They also tend to be mechanically unstable in water. The layers can just float apart unless you use special methods to kind of staple or cross-link them together.
So incredibly fast flow, but not selective enough or stable enough for full desalination. Yeah, what's the future potential here?
The potential is still significant if these issues can be solved. Researchers are actively working on ways to decrease that interlayer spacing and make the frameworks more robust. Things like chemical or thermal reduction to remove those oxygen groups that cause swelling, or using covalent cross-linking to lock the layers together at a desired smaller spacing.
And if they succeed?
If they succeed, these membranes could become really useful for nanofiltration NF range separations. NF is great for removing larger ions like calcium or magnesium and some organic contaminants. Still not quite the full seawater desalination level of selectivity, but a very promising intermediate step towards highly selective and highly permeable membranes. 5. Smart strategies. Innovative system designs, and fouling-resistant surfaces.
Okay, given that just making membranes more permeable has, let's say, diminishing returns on energy savings for the main RO step, what other system-level innovations are researchers looking at? To make a real dent in energy use and overall efficiency, we need to look beyond just the membrane material itself, right?
Exactly. The focus broadens to optimizing the entire process, the whole system configuration. One really promising approach is called staged membrane operations. Sometimes you hear it called pass-by-pass systems.
Staged operations, meaning not doing it all at once.
Right. Instead of one big RO stage operating at a single very high pressure, you use 2 or more stages in series. The first stage operates at a lower pressure and gets maybe a lower percentage of water recovery from the feed.
Okay.
Then, the concentrate of the brine leaving that first stage, which is now saltier but a smaller volume, is then repressurized, often to a higher pressure, for the next stage. And you might even have a third stage.
Why does that save energy?
Because it allows smaller volumes of water to be brought to progressively higher pressures. You're not pressurizing the entire initial feed volume to the maximum pressure needed for the final concentration. Theoretically, this reduces the overall energy consumption for the RO step itself.
Can you give an example?
Sure. For typical seawater desalination aiming for 50% recovery, we said a single-stage system has a practical minimum energy around 1.56 kilowatt an amicamp. A well-designed 2-stage system could theoretically bring that down to around 1.28 kilowatt an amicamp.
That's a noticeable saving.
It is. Now, it does add complexity. You need more pumps, more membrane modules, more intricate plumbing, which increases the capital cost, but it brings the actual energy use much closer to that fundamental thermodynamic minimum we talked about. It's about optimizing the pressure profile across the whole system.
That makes a lot of sense. What about using energy that's currently just wasted. That seems like a really smart approach, especially for industries that generate a lot of heat.
Absolutely. Waste heat utilization is a huge and still largely untapped opportunity. Think about power plants, chemical factories, steel mills.
Yeah.
They all produce substantial amounts of low-grade waste heat.
Heat that's not hot enough to make electricity efficiently.
Exactly. But it's often more than hot enough to drive certain desalination processes. Technologies like forward osmosis, or FO, are particularly well suited for this.
Forward osmosis. How is that different from reverse osmosis?
Okay, in FO, instead of using high hydraulic pressure to push water out of the saltwater, you use a special draw solution. This is a highly concentrated solution with a very high osmotic pressure.
And it does what?
It naturally pulls water across a semi-permeable membrane from the seawater, driven by the osmotic pressure difference, like water moving towards a saltier solution. The key difference is this step doesn't require high hydraulic pressure.
So much lower electricity use for that part.
Significantly lower electric energy footprint, yes. Now, once that draw solution gets diluted with the pure water it pulled from the seawater, you have to separate the pure water from the draw solution solutes.
How do you do that?
That's where the waste heat comes in. You heat the diluted draw solution using that low-grade waste heat. This separates the pure water, and the draw solutes are then concentrated again and recycled back into the system to pull more water across.
So the main benefit isn't necessarily lower total energy, but much lower electric energy, making it cheaper if you have free waste heat.
Precisely. The total energy input, including the heat, might sometimes even be slightly higher than RO. But the electric energy consumption, which is usually the most expensive and carbon-intensive part of a desalination plant's running costs, is dramatically reduced. This makes FO really economically attractive in places where you have a readily available, low-cost waste heat source nearby.
What kind of draw solutions work for this?
Researchers are exploring various thermolytic draw solutions, ones that can be easily separated using heat. A common example being explored is mixtures of ammonia and carbon dioxide. These can be separated and regenerated using heat below 60 degrees Celsius, a temperature easily found in many industrial waste streams. Imagine a power plant co-generating electricity in fresh water using its own waste heat. That's the kind of synergy we're looking for.
Very smart. Now let's circle back to that really persistent, costly problem we keep mentioning, fouling. Since it's such a major operational headache, what are the cutting-edge ways to design membranes that actively resist getting fouled up right from the molecular level?
Yeah, the fight against fouling is absolutely critical, and it's a huge area of research. A lot of studies have looked at what makes a surface inherently resistant to fouling, and some common characteristics have emerged.
Like what?
Surfaces that resist fouling well are typically very hydrophilic. They love water. They tend to have lots of hydrogen bond acceptors on their surface. They're generally electroneutral, meaning they don't have a strong positive or negative charge. And critically, they usually lack hydrogen bond donors.
Why those specific properties?
These properties work together to help the surface create and hold on to a stable, tightly bound hydration layer, a layer of water molecules right at the surface. This hydration layer acts like a physical, steric repulsive barrier. It basically prevents organic molecules, proteins, bacteria from getting close enough to actually stick to the membrane surface.
Okay, so how are scientists taking that knowledge and applying it to make our current TFC membranes better at resisting fouling?
One of the most promising and versatile strategies is using advanced surface grafting techniques. This involves chemically attaching specific water-loving polymers directly onto the membrane surface. Polymers like polyethylene oxide, PEO, or things called zwitterionic polymers, which have both positive and negative charges, but are overall neutral.
So you're basically adding a fouling-resistant coating.
Kind of, but it's more sophisticated than just a coating. Advanced polymerization methods like atom transfer radical polymerization, ATRP, give incredible control. You can precisely control the density, the length, even the architecture of these grafted polymer brush layers.
Polymer brushes.
Yeah, imagine tiny hairs sticking up from the surface. This level of control lets you create surfaces with extremely low water contact angles, sometimes less than 10 degrees, super hydrophilic, which translates to practically zero absorption of biomolecules like proteins, and much less adhesion of other fulans. And crucially, these modifications are designed carefully so they don't significantly hurt the membrane's water permeability or salt selectivity.
That sounds incredibly precise. What are the main challenges in actually doing this on an industrial scale for millions of square meters of membrane?
It's definitely challenging. First, you need to get those initiator molecules anchored uniformly and densely onto the typically rough surface of the TFC membrane. That's tricky. Second, you need to ensure these grafted layers are really robust and stable long-term, especially considering they'll face harsh chemical cleaning cycles. And third, scaling up these very precise lab techniques to be cost-effective for large area industrial production is always a major hurdle, moving from milligrams in the lab to tons in the factory.
What about for those porous membranes, like UF membranes, where fouling happens inside the pores too? Just grafting the outside surface wouldn't solve the internal fouling problem, would it?
You're exactly right. For porous membranes, surface crafting alone often isn't enough because those internal pore walls, which make up a huge amount of the total surface area, can still get badly fouled irreversibly. So for those, a more elegant approach called in situ surface segregation is often used.
In situ surface segregation, how does that work?
It's quite clever. You blend a specially designed amphiphilic copolymer directly into the main polymer solution before you cast the membrane.
Amphiphilic, meaning it has two different parts.
Exactly. It typically has a hydrophobic anchor part that likes and mixes well with the bulk polymer of the membrane itself. And it has hydrophilic side chains that love water and resist fouling.
Okay, so you mix this special polymer in, then what?
Then, as the membrane is actually being formed, as it precipitates and creates its porous structure, something neat happens. The hydrophobic anchor parts make sure the copolymer gets locked firmly into the membrane matrix, but simultaneously, those hydrophilic water-loving segments naturally segregate. They migrate and orient themselves towards all the polymer-water interfaces throughout the entire membrane structure.
So they automatically coat not just the outside surface, but the inside walls of all the pores too.
Precisely. It creates a uniform, fouling-resistant surface throughout the entire membrane, including deep inside the pore network. The membrane essentially builds its own anti-fouling layer from within as it's being made.
That is remarkably smart. Are there examples of this working well?
Oh yes. A classic example used pan-graft PEO, blended into polyacrylonitrile, pan-UF membranes. These showed basically complete resistance to irreversible fouling by various nasty organic fluents. And even more advanced designs are emerging now using ternary block copolymers.
Ternary, 3 parts.
Right. These have blocks that provide not only excellent fouling resistance, the hydrophilic parts, but also fouling release properties from special low-surface energy blocks. This means that even if some foullants do manage to stick on temporarily, they can be much more easily washed away just by the fluid flow, reducing the need for harsh chemical cleaning even further.
And one last critical point about current membranes. Their sensitivity to chlorine. That's a big operational limitation, isn't it? How are these next-gen approaches addressing that?
Yes, this is a really important practical point. Current TFC polyimide membranes are notoriously sensitive to damage from oxidants like chlorine, which is ironically a very common and effective disinfectant used in water treatment.
So you can't use chlorine to clean them or control biofouling easily.
Exactly. This sensitivity severely limits the cleaning options operators have. It also means they have to add expensive and complex pre-treatment steps just to rigorously remove any trace of chlorine from the feed water before it even touches the RO membranes.
What about future membranes?
Many of these future membrane designs, whether they use different chemistries or have protective surface layers like those grafted polymers, are being engineered to be much more oxidant resistant. This fundamental improvement would be a huge benefit. It would allow for much better, more aggressive control of biofouling, which is a major challenge by enabling effective chlorine cleaning when needed. This should lead to more stable, more reliable, and longer-lasting membrane performance in real-world plants. 6. Environmental footprint and the sustainability outlook.
Okay, we've covered a lot of ground on the incredible science and engineering of making salt water drinkable, but as with any big industrial process, we absolutely have to ask about the environmental footprint. Are these desalination plants truly a sustainable solution, or are we just, shifting environmental problems around?
That's a vital question, and definitely one that's at the forefront of ongoing research, engineering design, and policy discussions. Let's break down the main environmental aspects.
Okay.
First, the carbon footprint. Current seawater reverse osmosis, SWRO, plants, which mostly run on electricity from the grid, often generated from fossil fuels, inevitably contribute to greenhouse gas emissions. State-of-the-art plants typically emit somewhere between 1.4 and 1.8 kilograms of CO2 for every cubic meter of fresh water they produce.
That's not insignificant. How do we minimize that?
The ultimate goal, clearly, is to directly power these plants using renewable energy sources, solar, wind, geothermal. Where direct connection isn't always practical, maybe due to intermittency, indirect approaches like investing in renewable energy projects to offset the plant's grid consumption can help balance the carbon books.
What about the direct impact on the ocean itself, where the seawater is drawn in? Does that harm marine life?
That's another major consideration, especially for large plants using open surface intakes that just suck water directly from the ocean. These can impact marine life in two main ways. First is impingement, where larger organisms like fish or crabs get physically trapped and killed on the intake screens. The second is entrainment,
Entrainment.
where smaller organisms, think fish larvae, eggs, plankton, are small enough to pass through the screens but get drawn into the plant's internal systems and don't survive.
Okay, so impingement and entrainment. How can those be minimized?
Several strategies. You can locate intakes strategically, maybe in deeper water, further offshore, where there's less biological activity. A really effective solution is using subterranean intakes, often called beach wells.
Beach wells, like drilling wells on the beach.
Essentially, yes. They draw seawater slowly through the sand and sediment, which acts as a natural pre-filter and virtually eliminates both impingement and entrainment. However, beach wells have limitations on the sheer volume of water they can supply, so they might not be feasible for the very largest mega plants.
Any other solutions?
Another smart approach is co-locating desalination plants with coastal power plants. Power plants already draw in huge amounts of seawater for cooling. The desalination plant can use the power plant's slightly warmed cooling water discharge as its feed water.
Ah, so you're using the same intake water twice.
Exactly. Yeah. It reduces the total volume of water being drawn from the ocean, minimizing the overall ecological impact.
Okay, intake addressed. What about the stuff that comes out of the plant? That super salty brine concentrate. What happens to that, and how do we manage its discharge safely?
The concentrate, or brine, is definitely a primary focus for environmental management. It's roughly twice as salty as the original seawater. Plus, it contains trace amounts of chemicals used in pretreatment or cleaning, like antiscalants or coagulants.
So you can't just dump it anywhere?
No, definitely not. This highly saline solution is typically discharged back into the marine environment, but careful management is key. Several strategies are used to mitigate its impact. One is dilution. You can mix the brine with other available wastewater streams, like treated municipal effluent, if available, to lower its salinity before discharge.
Makes sense.
Another crucial technique is using highly efficient diffuser systems at the discharge point. These are specially designed outfalls that ensure the brine mixes rapidly and disperses quickly into the larger body of seawater. The goal is to prevent creating localized hotspots of high salinity that could harm marine life near the outfall.
And where you put the outfall matters too.
Yeah. Absolutely. Careful site selection is paramount. You want to choose discharge locations with good natural currents and mixing favorable hydrodynamics that help dissipate the salinity quickly. And critically, you must rigorously avoid discharging near sensitive ecosystems like coral reefs, seagrass meadows, or mangrove forests, as they're particularly vulnerable to salinity changes.
So while there are concerns, there are ways to manage them.
Yes. While we could always use more long-term experimental data on the cumulative impacts, the widely accepted view in the scientific and engineering community is that significant adverse environmental impacts from brine discharge can be largely avoided with proper, thoughtful design, meticulous site selection, and diligent, ongoing management and monitoring of the discharge.
Okay, so looking ahead then towards this vision of a more water-secure future, where does research and innovation really need to focus now to make desalination even more sustainable, even more widespread as a solution?
Well, as we've really hammered home today, the core desalination step in RO is already remarkably efficient. It's bumping up close to its practical minimum energy requirement. Therefore, the most significant, truly transformative energy improvements moving forward, they're going to come from fundamentally reducing the energy demands of those ancillary stages.
Especially pre-treatment and post-treatment.
Primarily those, yes. This means developing those incredibly fouling-resistant membranes we talked about at length. Membranes that can handle diverse, maybe less filtered feedwaters without needing those extensive energy-guzzling pre-filtering steps.
And membranes that are more selective.
Exactly. Creating membranes with much higher and more precise selectivity for specific problematic small neutral species. Boron is the classic example, but also things like trace pharmaceuticals or pesticides. Membranes like that could eliminate the need for those extra energy-intensive RO passes that are sometimes required now to meet very strict water quality standards for agriculture or drinking water.
And you mentioned molecular simulation as a key tool in getting there. How does that help speed things up?
It's an absolutely game-changing tool. Molecular simulation allows researchers to computationally model and predict how different membrane structures, different chemistries will perform right down at the atomic and molecular level.
So you can test ideas on a computer first.
Precisely. Before undertaking costly and time-consuming physical synthesis and testing in the lab, we can predict water transport rates, salt rejection, even estimate the fouling propensity of completely novel materials. This in silico experimentation, doing experiments on the computer, provides invaluable guidance for designing materials with the exact structure and chemistry needed for optimal performance. It dramatically accelerates the whole discovery and development process.
So the grand vision, desalination isn't just an option, it's really a crucial piece of the puzzle.
Absolutely. Especially when it's integrated intelligently with other smart water management strategies, things like rigorous conservation, efficient distribution, intelligent water reuse. Desalination isn't just an option, it's really an indispensable, crucial component in meeting the world's growing, undeniable demand for fresh water. It represents a steady, abundant, climate-independent source of high-quality water. Water that can sustain agriculture, support growing populations, and promote robust economic development in water-stressed regions for, hopefully, generations to come. Outro.
Wow, so we started this deep dive asking a pretty big, maybe audacious question. Can we really drink the ocean? And I think as we've explored today, the answer is a definite resounding yes, thanks to some truly astonishing scientific and engineering breakthroughs over the decades.
The progress has been remarkable.
It really has. We've journeyed from understanding the almost invisible dance of molecules inside those perfect aquaporin channels in nature to the incredibly clever ways scientists are designing entirely new materials, literally from scratch, and even rethinking entire system designs to tackle this profound challenge of global water scarcity. It's genuinely a testament to human ingenuity and that relentless drive to find solutions.
And remember, for those of you listening who might be just starting your college journeys, embarking on your studies, your generation will inherit and shape this future. These interconnected challenges, water scarcity, energy needs, environmental sustainability, they are among the most pressing and complex challenges we face as a planet.
And the solutions aren't simple.
No, they lie not just in one single field, but in continued interdisciplinary innovation, in rigorous critical thinking, and honestly, just in having a deep-seated curiosity about how the world works and how we can potentially make it better. So stay curious about the world around you. Ask questions. Because the next big breakthrough, whether it's in clean water or clean energy or environmental solutions, it might just come from someone exactly like you.
If you enjoyed today's deep dive, don't forget to subscribe to our channel for more explorations from the EON Nexus Lab.